Well, delighted to be back in Iowa City, and I want to thank the organizing committee for inviting me. I wouldn't have missed this event, even if I were coming from Athens. Of course, it turns out that I actually came from Jerusalem on Wednesday, but it's Don and I go back a long ways. We actually got our PhD the same year. We coexisted in many conferences together. And excuse me, I think I may have picked up the wrong version of the presentation. Yeah, I did. As I listened to people talk today, I kept revising my presentation. And one more thing. There's a final and then the revised final. Okay, so needless to say, I didn't have very many pictures, and I didn't want to let you know that so about some of the things that Don said. This is a picture from the Mariner 4 flyby of Mars in 1965. And Van and I are looking intently at something, as you can see. And that happens to be a strip chart recorder that Don talked about, as we were watching at 8 1/3 bits per second. Trying to see what, if anything, our Geiger counter and solid state detector were saying. It was my first instrument that I built when I came to Iowa City. And this is another picture with Tom Armstrong, who is here, for the Explorer 33 instrument that we had just built. This goes back to 1965. But I also came to Iowa in a way similar that Ted mentioned earlier, namely that I was an undergrad when Sputnik went up, first year undergrad at the University of Minnesota. And I became intensely interested in getting into the space program. And at the time, after a couple of years, I worked for Professor Winkler of Minnesota, who was also involved in a program to fly balloons to look at solar cosmic rays at the time. And I used to go out and fly balloons. And I made, my specialty was to make ion chambers. So Van Allen visited the campus in 1960, and needless to say, to talk about the Van Allen belts. And Winkler brought him to the laboratory, and I happened to be at my bench trying to make an ion chamber play, and he stopped by and says, "Oh, what are you doing?" And I said, I'm making an ion chamber. And he says, "Well, how does it work?" And I did my best to explain to him how the ion chamber worked. Of course, I realized that he was giving me an oral exam at the time. And he said, "Well, are you planning to go to grad school?" I said, I like to. I said, "But I don't have any money, so I think I'm going to get a job." He says, "Why don't you apply to Iowa?" I said, "Well, sure, okay, I'll apply." And I did, and I got an assistantship or a fellowship, I can't remember which. So here I was in the fall of '61 in Iowa City, Iowa, and the rest is history. But we are here to talk about Don's contribution and all the great things that he did and all the things that I learned. I'm sure you've heard this already, but this is one of the nicer schematics with a Whistler. This, I think, is from Cassini, if I'm not mistaken. And it's a nice schematic because you see it shows the lightning, and then you hear the Whistler, and you see the trace. And of course, that is not the only sound that he produced. I think this was the first time where actually one could hear the plasma. And the one that's my favorite is this, this one from musical tones associated with the rings. And they're really musical tones. I mean, it's amazing when you sit and listen. You say, well, maybe a composer did this. Some of the modern composers, well. So, but one of Don's principal characteristics is he is not just recording the sounds, but he always is the fact that he always gives a physical explanation. And this is, I think, the first sketch that I remember with the proposal that this was from micrometeoroid impact, probably micrometeoroids, not meteoroids, on the rings. And what you would expect is a plasma cloud, and then you have Huisser-Moll resonance cone, gave the equation, and this is sort of characteristic in the way he worked. He always presented the physical picture with what the underlying physics was for this kind of work. And of course, you have already heard about auroral kilometric radiation, and this should have started. And this is one of the better ways that he mechanized the whole thing. And you can actually hear the auroral geometric radiation and the periodicity. And that has become a very big deal with Cassini. Of course, Bill talked about this earlier in a more comprehensive way. And this story whereby we could hear the sounds of the plasma, but never see a picture, which the people who do planetary geology have it all over us. They always showed pictures for what they were observing, and gave us a lot of food for thought on how we could actually visualize the invisible. How can we actually see a plasma? And this is an image, composite image of the magnetosphere of Saturn, which we had before Cassini. And you see, all of this has been built from observations that through the passage of Voyager through the system, and in a way from analogy from Earth. But we really didn't know for sure about these structures. We had a measurement here, a measurement there, a measurement over there, a measurement over there, and then we infer the rest. So we came up with a technique to actually see all of that. And it goes with a magnetic field line, and you have an ion that is gyrating around the field line, and it runs into a neutral atom. And what happens is that they exchange an electron. And all of a sudden, this ion has become neutralized and is freed from the magnetic field, and it shoots out. Whereas the electron is now the remaining, the neutral atom is now stuck, but close to the magnetic field because it didn't get much energy out of that. So what, with the electron transfer, the energetic neutral atom heads out, the low energy electron gets stuck, and as it goes out, it runs into our ion and neutral camera, which is the detector that we designed to really do an image, but instead of using photons, to use neutral atoms. But these were energetic neutral atoms. And the principle was fairly simple. What you do is you get a time of flight system where you have a foil here, a foil there, sometimes a solid state detector behind, and we charge a number of plates, positive and negative, so that when a charged particle comes in, it runs into these plates. But when a neutral atom comes in, it hits this foil, it generates a secondary electron, and you have the start of the time of flight. And then it hits at this point, and again, it generates a secondary electron. So we do 2D imaging of where all these neutral atoms that before were ions, and they came from a place in the magnetosphere of the planet. And that's how we make images. So the basic, the thing, what one measures, this is another way of showing schematically what I just talked about. What we measure is the intensity of energetic neutral atoms. Has to do with the charge exchange cross-section between the ion and the neutral, the intensity of the ions that are trapped, the density of the neutrals, and the line of sight. So it's a line of sight integral. And the principal quantities are, suppose you have a spectrum like this, an energetic, of energetic ions, Cassini, which is what we kind of observe. And now you have a charge exchange cross-section, and you can see that the charge exchange is fairly large for all of these collisions, protons on methane, protons on nitrogen, protons on atomic nitrogen, on molecular nitrogen. But you want to do this below 100 keV. Otherwise, at the higher energies, the charge exchange cross-section drops quickly, and the intensities of the energetic ions you get also drop quickly. And actually, this did work. And here is our first image that we got as we were approaching the magnetosphere back in 2004 with Cassini. And we saw a variability in time between the night side and the day side. So, and this is the solar direction, this is the morning direction, and so on. And that's the intensity scale. Now, that was not the only part of the image we saw. Another part of the image was, this is the data projected on the sky. This is the main radiation belt that I just showed you. But we also noticed that there were these emissions very close to the planet, just above the equator. And the way we interpreted that is that you have energetic neutral atoms that shoot inward, they charge exchange, and then they move out again. And that's what we see as it turned out that we have a pretty solid interpretation that there is a radiation belt inside the D-ring of Saturn. And as some of you know who are associated with Cassini, when the mission is expected to end in 2017, we're going to place a spacecraft in an orbit that will take it inside the D-ring. And now we're going to do in situ measurements and see how true the inference of a radiation belt inside the orbit of Saturn really is. Anyway, the other thing, of course, that we do is that we actually can make movies. This is the direction, the solar direction, and we can see dynamics. All of a sudden, there's a big blow up, and it starts rotating in the direction of rotation of the planet. This is our field of view, of course. And we have lots of these. And the important thing is to try to make sense out of that. And it's also a lot easier once you are above the equatorial plane, where you can actually see the rotation throughout the day and night side, and 360 degrees. Well, what does all of this show when you look at the emissions? This is a period of about 10 days or so, 9 days. And you can see that the energetic neutral atoms oscillate with a period which is similar to that of the rotation of the planet. and so do not only the hydrogens. This detector can also see the oxygens, and they also oscillate in the same way. But what else do they correlate with? Well, the magnetic field oscillates SKR, so Saturn kilometric radiation, as well as the energetic electrons. So the whole magnetosphere is pulsing, and the question is, can you really see at least the plasma rotate? This is one image on the left that shows the ring current. Once the spacecraft goes above the plane, we could actually image the ring current around the planet. And you can actually see, this was a still. This is the actual rotation. And typically what happens is, by the way, X is in the solar direction. And then we have these pink arrows that are rotating with the planet. And one of the things you can see, well, there are two things. First, that when this activity begins, it usually begins near local midnight, and then it starts rotating with the planet, but not exactly at the rotation of the planet itself. Sometimes it lags, sometimes it goes faster. By the way, that's I don't know if you noticed the name, ion and neutral camera. We can claim that we know exactly what took place, where it took place, and when. And this is a unique capability, I think, that brings a lot of understanding into the dynamics of magnetospheres. I'm going to proceed. Now, okay, this is the ring current, but how is that connected to the overall system? And we have instances where that we have imaged that as well. What you will see here is, this is a schematic that I will show you the dynamics. This is the aurora at Saturn taken with the UV's instrument, the UV aurora. These are the clouds of charged particles in the ring current that rotate. And what I will show you, I mean, you can imagine that there is a connection here between the equator and the high latitudes in the aurora. We have clearly field-aligned currents at Saturn. And so if this works, this is the aurora kilometric radiation from RPWS. So we repeat, notice, this is where the explosion happens on the night side. And this starts, the whole plasma cloud starts rotating. So does the auroral emissions that become intensified. You can imagine the connection here. And then it goes through the day side, the aurora kilometric radiation. And then it peters out by the time it gets all the way around to the day side. So this is, I think for the first time, we have a way of having the whole picture of what actually happens when you have substorms. And I want to show you this particular image. We found that out fairly early, where these are successive images with the energetic neutral atoms. This is the magneto tail. You see the beginning of something. This is beyond the orbit of Titan, by the way. And it intensifies. It calcifies, and it starts rotating. Sorry. And then it dies away. So this is a real Saturnian magnetospheric substorm. And many times it's really amazing what happens. Please watch this, what's going to happen. Here's on the midnight side, it starts rotating towards morning, noon. It reforms. goes away, then you see again that when it gets to this point, it becomes very intense. And all of a sudden, you will see something else. I think it's in the next round. This is, of course, several rotations of the planet. This has intensified, but notice what happens. From the tail, there was this plasma cloud that moved right into the orbit of Titan and passed it. So you can really see the dynamics. And from all of that, what we have done is, of course, we made a composite picture of, with, in this case, greater than 3 keV particles, which correspond to most of the energy density of the system. And you can see here that the tail is somewhat tilted, that on the day side, the plasma sheet is fairly thick. On the night side, it's quite thin. Then when there is, when the plasma rotates to the afternoon side, we find a lot of plasma in the magnetosheath and then upstream in the solar wind. And we know that originates from inside because not only do the spectra look similar, but a lot of the stuff that comes out here is mostly O+, oxygen, which doesn't exist in the solar wind. So it's a very clear indication of what we have. So far, that's the Cassini work. And you heard what the plasma wave sounds contribute to all of this, the aurora thermometric radiation, the sounds at the rings, the whistlers, and we're all become, by now, experts to read the colorful diagram that Don and Birker put in front of us. Even a lot of the planetary geology types are intrigued when they see this. Now, let's move, though, because Don's contributions have been much more than just the magnetospheres. I wanted to show you this schematic from the Voyager 1 data the last 3 years when, as you know, we had a discussion of is Voyager 1 in or out of the heliosphere. And the issue was that if you looked at the magnetic field, which is in the solar wind, is the Archimedean spiral. Presumably, this is upstream. And what happened is that the measured magnetic field was very close to the Archimedean spiral. The interstellar magnetic field is supposed to be like this, up and down. So that was one of the inconsistencies that was part of the difficulty in interpreting whether we were in or out. And furthermore, things got complicated by the fact that galactic cosmic rays were not isotropic outside in the medium that we were in. And everybody knows that Fermi acceleration tells us that everything is isotropic in cosmic rays. And what we found is that perpendicular to the magnetic field, you had these ups and downs in the intensity, but parallel to the magnetic field, everything was constant. So why is that? In the galaxy, things are supposed to be pretty straight. Well, there was one other measurement, of course, that was very important, and that is what is the density out here where Voyager was. And as many of you know, the plasma instrument on Voyager 1 is not working. So the only density that one could measure is if there were some electron plasma oscillations that will be measured by the plasma wave instrument. And sure enough, this is a diagram that, let's see if we can get this going. Oops. I'll do it again. There we go. No. Uh, it's an, I know what I'm going to do. It may not work on the image. I'll try. Ah, thank you. So that's the sound of electron plasma oscillations from Voyager. It started in November of 2012. Remember, we crossed on August 25, and then November, and then you see the density. And the density here, the density scale, shows that we were at about 0.1 per cubic centimeter, which is what the density is expected to be in interstellar space. And we had a meeting at the Applied Physics Laboratory in September, where we discussed all of this and whether we were in or out. I don't know if you remember that, Don. And, a lot of discussion. By the way, these are the 4 instrument PIs, and as you notice, some of us are getting a bit old. But we do have some colleagues or friends, Bill, Rob Decker, others who are keeping us in business. And this lady, you see, by the way, there's only one lady in the whole place. And she is the program manager, which means that she's highly respected because you all heard of the golden rule, whoever has the gold makes the rules. And so we decided what the picture really was. And this is a sort of a colorway of the whole thing. This is the direction of the sun. Here is the high-speed solar wind. We crossed the termination shock on December 16, 2004 at 94 astronomical units. We got into the heliosphere. The solar wind was slowed down. And then at 113.5 AU, we noticed that the velocity, the radial component of the solar wind went dead. There was nothing there. It just seemed like a swamp. And this lasted for several astronomical units. We call that the stagnation region. And then finally, on August 25, we crossed this boundary, which we said was the heliopause. And the October-November time frame is when the first electron plasma oscillation showed up from the PWS instrument. And as Don interpreted that, that was the density measurement that we lacked. So there was, as many of you know, a publication of in Science with Voyager on the cover and all these papers. Don's came in September. But it was a key measurement. The previous data were very good, but I think, in my judgment, the density measurement clinched it. So just, was it last month? There was this paper that Don led that we had more episodes of electron plasma oscillations, and I'll show you that. But let me explain this plot here. This is cosmic rays, and we crossed, and the cosmic rays went up, as they were supposed to do in the galaxy. The anomalous cosmic rays, which reside in the heliosphere, went down, as they were supposed to do. Here is what I described to you earlier. This is the LHCP measurements. The particles, the cosmic rays, parallel to the magnetic field, stay put. The ones perpendicular to the magnetic field. And by the way, we measured that because we took a big risk and placed the instruments for LHCP on a spinning platform, not a spinning platform, but a scan platform that moves 45 degrees every few tenths of seconds. And at the time, my friends, my engineering friends at APR said, "You're crazy. This thing is going to get stuck after 6 months. It's a crazy thing to do. But we did test the system for 250,000 steps because the expected lifetime or the expected mission was going to be Voyager to Jupiter and to Saturn. That was 4 years. And 250,000 steps is what we expected. We life tested it to 500,000 steps. So I have to tell you, this data comes because we have this stepping around. And we're approaching 7 million steps. And that little bugger, after 38 years, you still keep scanning around. Sometimes you're lucky in this business. But back to this diagram here. And you can see that the cosmic rays become isotropic now and then. And there was a shock here from the magnetic field data. Here, they became isotropic again, but there was no shock. Here, we started having the same kind of anisotropy. There was a minor shock, and they became isotropic. And I hope this is going to work. There. So this is what I showed you before, Gurnett's sounds. This was in April. And then silence for well over a year. And then in February, August, so you can hear it again. The plasma wave was G. The density hasn't changed. Now, I will conclude by a diagram that Don hasn't seen yet. But it's what happened after this point. And we now have in the Gurnett et al. Paper an explanation of what is happening and why. And here is the latest data as of Monday. So I had shown you the data up to this point. That's what that paper was based on. And here's what happened afterwards, up to this point. Right after the paper was submitted, there were indications that something was going to happen again, and we started seeing the cosmic rays decrease perpendicular to the magnetic field. We also thought that the amplitude of this decrease would get smaller and smaller as we went farther away from the heliopause. You see, this was the biggest one, next one was smallest. We thought, well, maybe the next one is going to be this big or something. Here it is. And it keeps growing, and it may be as large as we have ever seen. And Don sent me an email when I inquired that I think it was the 5th of September when you began to see electron plasma oscillations. So electron plasma oscillations here when at the anisotropy is very large. Electron plasma oscillations here when it's isotropic. Electron plasma oscillations here when the reversal begins. Electron plasma oscillations when it starts. Electron plasma oscillations when there is a shock. So the story is evolving. And finally, I'd like to comment on the synergy between Voyager and Cassini. As some of you know, because of energetically neutral atoms, not only can you take images of the magnetospheric plasma, but you can also take images of the heliospheric plasma. And we have done that, and IBEX has done that at lower energies. This is the image from 2014. And what we have done here is watched the ions from Voyager. And these are plotted here. And you can see that they do change. This is Voyager 2. The red is Voyager 1. And then we have an image of the heliosphere from Cassini. And Voyager 1 is right up here. I don't know if you can see it. Voyager 2 is down here. And there are two things. First of all, on top, you see that as the, let me just pick on this one, which is very clear, as the intensity of ENAs decreases, so do the ions. And when they began to recover in 2013, so did the ions at Voyager 2. Voyager 1, of course, is out. I say, Len Fisk is going to disagree with me, of course. But what is seen is that what we deduce from that by having measurements remotely and with Voyager in the plasma seed, and they remote and in situ go up and down together. And the only way we can interpret that is that these energetic neutral atoms come from the helioseed, where Voyager is, not from outside into the upstream medium. And we are anxiously awaiting the new data, because you can see that not only they go up and down together, but this intensity of ENAs and of ions in the south hemisphere has recovered from solar minimum, but in the northern hemisphere it has not. So I think there is no model that at the present time explains that situation at all. And I just want to show you again, to emphasize the fact that it looks like after solar minimum, the heliosphere, the helioseed, does not recover uniformly. The south helioseed recovered, the north helioseed has yet to recover. And finally, I will conclude with this slide, which is from the Aero Club of Los Angeles about 1.5 years ago. And Don, as you can see, there are at least 2 other people that are crazy enough to work long after they should have been retired. And Ed Stone accepted the award from Voyager, from the Aero Club for Voyager 1. And there are many more in this room. So may your life be just as exciting in the next 50 years as it has been so far. Thank you very much for all you have done for the discipline.
Thank you. We have some time for a couple of questions. Comments? Yes, please.
It was difficult to read your chart from back here, but did you establish the heliopause at 126 AU?
The heliopause at 121.6 is what we're crossing. But like I said, there are some at least 2 people I know who say, no, we're not out.
For a layperson, that's an interesting number, but I wonder, is that accepted these days now?
As I said, everybody but 2 people. One of them is in the audience.
I'm pretty quiet.
Tom was here, was it 2 years ago? And he received a very prestigious award from the University of Alumni Award. I will frankly say I don't remember the name of the award.
Alumni fellow, I didn't know either until we notified.
Anyway, so he was here recently for that. And the second comment I'm going to make is that in Science magazine, maybe 3 or 4 weeks ago, there was a long article you might want to find it about Tom Krimigis as being the only principal investigator, I'm trying to state this accurately, that has visited and instruments go to all of the planets, counting Pluto.
Yes.
Thank you. I'm close.
Yeah, well, it's based on investigating, you know, my first one was Mariner 4.